Good morning. I am Krishna Kumar. I'm sorry I could not enter the Google Classroom because of some technological problems, a lot of operating system problems and so on. But I will sort it out in due course. But let us continue with our lectures. Now, this is what is called this time the main theme is the Gronwall's inequality. This is actually one of the tools that we use very frequently while working on the existence theory. Now, just recall what we did. We had this equation y derivative equal to, I was using this notation, f of xy defined over some open connected domain. Then we had this, the initial condition. So this is the initial value problem. And of course here x naught, y naught belongs to. So this is the problem that we will be working on. And the geometry is this. This is D. And in D some, okay, this need not be a bounded domain or anything. In D you have a point x naught, y naught given. And then we had of course you had a rectangle R. This is a closed bounded rectangle, and this is defined as xy with mod x minus x naught less than or equal to a, mod y minus y naught less than or equal to b, and a and b are chosen such that R is contained in D. This is possible because D is open connected and this is an interior point, therefore this is possible. Now what we do is we look at the following. So we define H. Okay, we choose an H possible. Now first of all what we did was we constructed an approximate solution using the geometric ideas. What we did was, see, you have, this is the point x naught. On the interval x naught minus h to x naught plus h, we constructed a solution. What are the solution? How did we construct it? We started from the point x naught, y naught, and we divided this into what you call subintervals. So just like partition the interval x naught plus h, and likewise you can do it on the other side also. Then we constructed a line with a slope f of x naught, y naught, and then we saw where it meets the ordinate, and then that point was named as x1, y1, and then we once again looked at the value f of x1, y1, constructed another line segment, and then we had something like this, and then at x2 we again took the ordinate and then mark the point x2, y2 and so on, and this way we constructed a continuous line but not necessarily a differentiable. It is not a differentiable line in general because there are points where it fails to be differentiable. On a finite set of points it fails to be differentiable. So such a line was constructed, and then we proved that we defined the concept of what is called an approximate solution. The approximate solution was defined as the following. So you have so we have chosen a epsilon positive, and then you had this solution, what you call, say, I don't know what notation I used last time. So I think I was using, I think I have taken yx to be, I've taken the analytical form of it. yi minus 1 plus x minus xi minus 1 into f of xi minus 1 yi minus 1. This part is the equation of the line that we constructed on the interval xi minus 1 to xi minus 1 to this is the line that we have constructed on this. Now you see that you take on the whole interval you define this, and then yi minus 1 is taken as y at yi minus 1 y at xi minus. This is the notation. Okay, so we now define on the interval x naught so you had on this interval we have constructed the line. Now you see that y derivative equal to f of yi minus 1 on the interval xi minus 1 less than x. At this point x1, x2, etc., the function is not differentiable. So there are a finite set of points on which it is not differentiable, and we proved that given epsilon positive, there exists an approximate solution yi minus 1 yx such that y derivative of x minus f of x is less than or equal to epsilon, except at finitely many points. Now this is what we proved. So there is an approximation. This is the sense in which you say that y is an approximation. This relation can fail at a finitely many points. I hope I am audible because of the heavy rain that's going on. There may be some disturbance. So that will be over as soon as the rain ceases. Okay. So let me now start working on the fundamental inequality. But before that, we will introduce the so-called Lipschitz condition. Before that, let me just take up a specific differential equation. We take y derivative equal to y to the power 1 by 3. This is defined on a d we take as the whole of r. So, and we have, that means f of xy is taken as y to the power 1 by 3. This is well defined as a real valued function. So there is no problem. It is also continuous. Now let us work out, and it's also differentiable. There is no problem, except possibly at some place where y equal to 0 or something like that. So we will take it up. Now we will look at the initial value problem. So this is our the domain on which we are working. This is the point 0, 0. This is the point which is taken as the initial value. Now what we are looking for is a function whose graph passes through the point 0, 0 such that it satisfies the given differential equation and the initial condition. Now this is what we are looking for. One can solve this, and you can immediately see that the solution to this equation is, that's very simple to solve. I think your elementary knowledge of solving differential equations should help you. So this is actually yx equal to is a solution of this differential equation. See, now what you observe is that this is our initial value problem, that is the differential equation with the initial condition x represented by the point 0, 0. You see that there are two solutions. The first solution is y identically equal to 0, defined for x belonging to infinity. There is a second solution that you can give. This is the one that I have defined here. That is yx equal to, or I will write it, you can easily see that this, just substitute this and you can easily see that it satisfies the equation. Of course, this you cannot use the same idea for x negative, because you have got x to the power 3 by 2 coming when x negative. This is not defined as a real valued function. That's why you are writing it on x greater than or equal to 0, x less than or equal to 0, less than or equal to 0. But at the same time, you see that at x equal to 0, it is well defined and it is differentiable. Okay. So the graph of the function is, there are two functions coming up as a solution for this initial value problem. Namely, this is x identically equal to 0. Then there is another solution which comes up as, which has a graph something like this. Okay. So this is a, you have a continuous function, nice function, y to the power 1 by 3. fxy is y to the power 1 by 3. It is well defined, smooth, nice, and everything. And you have the differential equation here. It's a perfectly legitimate initial condition. But you see that the problem is there exists a solution. However, there exists more than one solution satisfying the initial condition. So there is no uniqueness. This is the problem. So the solution is not unique in this case. So if the moral of the story is this, if you have an initial value problem, y derivative equal to f of xy, y x naught equal to y naught, and with the assumption that f of xy is continuous on the domain D, then with an initial condition you may be or may not be able to get a unique solution. Both are possible. So just continuity on f alone is not going to tell you that there is a unique solution. So you need some more additional restrictions on that function. So we will leave it there at the moment and then come back to this example again. And why this phenomena of a second solution emerging with the same initial condition, this is something that we will investigate. So in this context, we will introduce the so-called Lipschitz condition. So what is the Lipschitz condition? We will, I think you may be familiar with. So we will define this definition. A function xy D is open connected, D open or, for this definition it can be even a closed domain, doesn't matter, is satisfy a Lipschitz condition with respect to y with Lipschitz constant k, Lipschitz constant k positive if for every x y1 x y2 belonging to D, modulus of is less than or equal to k times this relation shows that it is, of course, continuity is straight away comes with respect to y is comes out from this. Okay. So what it says is this: suppose xy1, this is xy1 and this is xy2. That means they are points on the same vertical line. The difference in the values of f at xy1 and xy2 is bounded by k times the distance between y1 and y2. So you see that this is obviously continuous with respect to the second variable. Anyway, we are assuming in all our cases that f is a continuous function, so that does not matter. But this is a larger restriction that you have. It's not that, see, there are functions which are continuous but not satisfying a Lipschitz condition. So I'll leave it as an example, as a exercise. It is continuous on D but not satisfying the Lipschitz condition. Okay, but not Lipschitz condition. But not so you have to fix your D. So this is a problem. So that I leave it to you. It's a simple exercise that you should be able to do. Okay. Now we will work out a theorem which will answer this question, but certainly it is nice to construct examples which do not fall into under this question. So we have a lemma. Has a partial derivative for y, bounded for all belonging to D, and D is convex. Then f of xy satisfies a Lipschitz condition for y the constant k is given by supremum of okay. What does it say? You have a domain D which may be open or now what we want to say is this: f is given to be a continuous function defined on D. And we also assume that f is bounded for all D. So these are the assumptions. Okay, it's a continuous function over D, need not be bounded. It is differentiable with respect to y on the whole of D, and the derivative is bounded for all xy belonging to D. And D is a convex region, which means, what does it mean? It means that if you take any 2 points, the entire line segment joining them lies inside D. That is the convexity. Then fxy satisfies a Lipschitz condition for y, where the constant k is given by k equal to supremum of df by dy. That is, you take the partial derivative, go for the bound of it, and call that k. And this is the lemma. Therefore, this is a very useful lemma, because if you, by taking derivative, partial derivative with respect to y, and then examining whether it's a bounded function or not, you can easily decide whether the function is Lipschitz or not. Now you can, I think I will give a local version at the moment, and this is something that you can use often. The function is said to be locally Lipschitz. What do you mean by that? Take a point xy at some interior point of D. There is some neighborhood in which the function becomes a Lipschitz, satisfies the Lipschitz condition. So this is what you mean by it is locally Lipschitz. It may not be globally Lipschitz, but it may be locally Lipschitz. I will give you examples of that. Okay, so it's quite easy to prove this. The proof is by mean value theorem. You have, by mean value theorem, you have f of x y1 minus f of, this is equal to xi, where y1 y2. So you are looking at this for a fixed x, you are looking at this as a function of y, and then you use this result. Therefore, what you have is this. Now you can easily see, you are assuming this is bounded, and you are assured that the entire line segment joining xy1 and xy2 lies in D. What is that? So this is, you are keeping the x coordinate the same. So this is xy1, and you are taking the vertical line on which you take another point xy2, and you are assuming that this entire line segment is on that, and therefore because of this assumption on the existence of the partial derivative, etc., now you see that you are assuming there is a bounded derivative for that, bounded partial derivative. Then this, on this line you have this particular result valid. This is the mean value theorem, looking at fxy as a function of y. Okay. Now it is quite simple that mod f of less than or equal to times, so this is taken as the Lipschitz constant. This turns out to be the Lipschitz constant. Okay, so that proves it. It's very simple. However, this is a sufficient condition. For example, even so, here you have an assumption that the partial derivative exists. So even if you don't have that condition satisfied, still the function may be Lipschitz. Now one example is this. You take f of xy to be equal to mod y. So let us take the function. I'll give an example where even if this existence of a bounded partial derivative is not valid, even if the function is not differentiable with respect to y, still the function may satisfy the Lipschitz condition. Give an example. Therefore, that example would suggest that essentially the lemma that we have proved is gives only a sufficient condition. So you look at this one, f of xy mod y. Okay. Now you see that for y equal to 0, it is not differentiable. Okay. Therefore, you look at this one. This function is Lipschitz. Why it is Lipschitz? So you take mod y1 minus mod y2 is less than or equal to mod. So with Lipschitz constant 1, it is Lipschitz. However, this function does not have the partial derivative. It's not differentiable at y equal to 0. The partial derivative does not exist for y equal to 0. So even if this condition is not satisfied, still it is Lipschitz. Now there is a slight a variant of this. Now here we have imposed a condition that D is convex, and D is convex has been used to ensure that the line segment joining xy1 to xy2 is lying inside D. Okay, So now we have a version of this by removing that condition. So you have lemma 2. If D is not convex, suppose D is not convex, let D be embedded in a larger domain D prime. Let delta be the distance between the boundaries C and C prime of D and D prime respectively. Let delta be positive. Then fxy, if fxy is continuous on D prime, assume df by dy exists and is bounded by n in D prime. Ellipsis condition. In D for constant k positive, where k is equal to maximum of n and l. Yeah. So the problem is this: we are now dropping the assumption that D is convex. So let us take a situation something like this. Suppose D is something like this. Okay. Now suppose this is embedded in a domain D prime. And D prime need not be bounded also. Okay. Right? Okay. So this is D is not convex, but it is embedded in a open connected domain D prime. Okay. Right. Now let C be the boundary of D and C prime be the boundary of D prime. Now you take the distance. What is the distance between two sets? Suppose you have two sets in a metric space. Then you can talk about the distance between the two sets. What do you mean by that? Suppose you have a set A, you have a set B in a metric space. Then what is the distance between A and B? This is equal to the distance xy, where x belongs to A So here we are looking for the distance between C and C prime. Okay. We have assumed that, so what you do is you take a point P on C and P on C prime. So let P be belonging to C and P prime belong to C prime. Then the distance between, then delta is taken as the minimum of distance between P and P. Okay. So for all possible Pn, P belonging to C, P prime belongs to C. This is what you call the delta, and we are assuming that delta is positive. That's the assumption that we have made. Now in such a scenario, what you have is this: you take x, y1. Now if you have your x, y1 and y2 and the entire line segment lies in D, there is nothing. You can apply the theorem that you have already proved. For such points you can apply this, and therefore you get, if you take df by dy and then take the bound on that, and that is n that we are assuming. Df by dy exists and is bounded by n in D prime. So we are assuming this is so in D prime. Therefore if it is in D, if it is contained in D itself, it is in D prime, and therefore you can use n as that. Therefore the k that emerges here will be n in that case. But we have a scenario where this may not be true also. See, your xy1 and xy2 may not lie inside D. I mean, there may be some spillover from there. But now what we can do is this. Okay. Yeah. So you see that this distance is then, whether it is in D prime or this line segment, whether it lies in D prime or not, can be even like this. You see that this is greater than the distance between the boundaries of D and D prime. That is for sure. Okay. So this distance, that is mod y1 minus y2, is greater than this. So let us write down that. So you see that, so proof. Let P1, which is x, y1, P2, x, y2 belong to. Then there are two scenarios that you can have. If mod y1 minus y2 is greater than delta, then you can easily see that mod f of x y1 minus f of x y2 divided by mod, and we have assumed that this is less than or equal to 2m. Why it is 2m? M is assumed to be the bound for f in D prime. Therefore, this is less than or equal to mod fxy1 plus mod fxy2. Each one is less than m. Therefore, this is this. And you have mod y1 minus y2 is greater than delta. Therefore, 1 upon mod y1 minus y2 is less than delta. Therefore, this is less than 1 by delta. And therefore, this is the number that you get. Okay. If then you are sure that the line segment P1, P2, this is the line segment, lies D prime. So we are not falling back on convexity or anything. And if mod P1 minus P1 P2, that is the distance between P1 and P2, lies inside D prime. That's clear. Okay, that's just, I don't think it needs any explanation, because you are assuming the distance between the boundaries of these two regions is less than or equal to delta. Okay. Sorry, is greater than or equal to delta. The distance between, when if you take 2 points on the boundary, then they are going to be this. So from that you can easily argue this, which implies once it is there, then you can use the fallback on the previous theorem. We have f of or if you want for clarity, I think I can put it this way. This is the Lipschitz constant that comes. And combining these two, it follows that it satisfies Lipschitz condition. So if you choose k to be the maximum of n and 2n. So under these conditions, all these things are accepted. I mean, you can have a look at this problem explicitly. Okay. So that tells you about the Lipschitz condition. Now we assume f satisfies Lipschitz condition and then prove certain results. And this in fact is something that is necessitated because of the example that we have looked at. So non-uniqueness of solutions may come up if we do not assume anything more than just continuity. Okay, so we'll have to put conditions on f. We are assuming a priori we are assuming f is continuous, We also have to put in some extra conditions, as we have seen the example fxy equal to y to the power 1 by 3. So we will come back to that example and then make more comments about it. So let me just go to the next main result. So we write down the fundamental theorem. So let me state this theorem and then we will work out the proof after a break. This is the or what you call a fundamental theorem. Okay, so let R, where R is of course the rectangle that we have considered in the construction of the approximate solution, in which continuous and satisfies a Lipschitz condition. With the Lipschitz constant let be admissible functions for satisfying y derivative equal to f of xy for mod x minus x naught less than or equal to h, with errors epsilon and epsilon. Now set Px or define Px as yx y tilde x and epsilon to be equal to epsilon. Okay, let me write this epsilon 1 and epsilon 2. So epsilon to be equal to epsilon 1 plus epsilon. Then mod Px is bounded by e to the power k x naught into mod p x naught plus epsilon divided by k. K is the Lipschitz constant. E to the power k into mod x minus x naught minus 1. So this is the mean inequality. This is called the fundamental inequality or Gronwall's inequality. Okay. So our objective is to prove this theorem. But before we go for a break, let me just look at the conditions. Okay. Let me just look at the statement of the theorem. So you have got the rectangle R. The rectangle R we take as we did in the previous result. What is that? That is taken as so we take some S to be less than or equal to where A and B are positive constants. Okay. Now let M be the bound Now this is in D. Continuity. Such a rectangular neighborhood you can always construct. Bound for F on S. That means mod Now we take R as the rectangle this is less than or equal to okay, we will first fix our let me first fix H. H you take define as minimum of okay. Now we define R as is contained in S. right? Therefore, so this is the rectangle R on which we have this point x0, y0, and that's how we have taken it. Okay. And we assume that f is continuous and satisfies a Lipschitz condition with respect to y with the Lipschitz constant k. So that's the usual assumption. Now we are taking two admissible functions for this. What are the admissible functions? The admissible functions are for mod x minus x naught less than or equal to h, assume x or rather we'll take it this way. F of is contained in D. Therefore, f of xy is defined. This is what we mean by this admissible function. And we work the two approximate solutions with errors epsilon 1 and epsilon 2 respectively, as we did in the construction, earlier construction, that is the broken solution that we have considered. Now we define Px to be a function yx minus y tilde x, and epsilon we set as epsilon 1 plus epsilon 2, the errors that you have there. Then what you have is that mod P is bounded by e to the power k into mod x minus x naught times mod P x naught plus epsilon by k multiplied by this factor, that is e to the power k times mod x minus x naught minus 1. Okay. So this is the result that we want to prove.